Hello everyone, welcome to the classroom of Basic Principles of Steel Structures. In this lesson, we will learn the strength and stiffness of members under combined axial forces and moments. This class includes the following main points. The first one is the definition of members under combined axial forces and moments. The second one is the strength of members under combined axial forces and moments. The third one is the stiffness of members under combined axial forces and moments. Firstly, let's learn about the definition of members under combined axial forces and moments. A member subjected to the combined action of axial force and bending moment at the same time is called a member under combined axial forces and moments. Figure 5.1 is a schematic diagram of members under combined axial forces and moments. In this figure, we can see that the bending moment of members under combined axial forces and moments can be caused by the eccentric force, the end bending moment, and the transverse load. When an eccentric force causes the bending moment, it is also called a member under eccentric load. Members under combined axial forces and moments are widely used in steel structures, such as beams and columns in steel frame structures and portal frame structures, and variable section columns in industrial buildings, and so on. A schematic diagram of a variable section column subjected to both axial forces and bending moments in an industrial building is shown in Figure 5.2. The diagram of forces on a beam column is shown in Figure 5.3. A schematic diagram of several cross-section forms of members under combined axial forces and moments is shown in Figure 5.4. According to the geometrical characteristics of the section, it can be divided into the open section and the closed section. According to the symmetry of the section, it can be divided into the single asymmetrical section and the biaxial symmetrical section. According to the section continuity, it can be divided into the built-up section and the solid web section. When the calculated length of the component is large and the load is large, the built-up section is usually adopted to improve the bending rigidity of the section. The selection of the section of the member under combined axial forces and moments depends on the use, load, fabrication, construction, amount of steel, and other factors of the member. The calculation contents of members under tensile forces and moments include the strength checking under the bearing capacity limit state and the stiffness checking under the serviceability limit state. The calculation contents of members under compressive forces and moments include the strength checking, the stability checking, and the stiffness checking. Stability checking should be conducted for both solid web members and built-up members. Both global stability checking and local stability checking should be conducted for solid web members. Considering the plastic properties of steel, the strength limit of beam columns under static load is the appearance of a plastic hinge in the section. Figure 5.5 shows the development of cross-section stress in a beam column with a rectangular section. With the increase of load, the development of stress on the cross-section experienced three stages: elasticity, elastic plasticity, and plastic hinge. Considering the plastic development of the section, calculate the strength of the beam column according to the elastoplastic design method. For unidirectional bending beam column, equation 5.1 is used to calculate its strength, while for bidirectional bending beam column, equation 5.2 is used to calculate its strength. Here, AN is the net cross-section area of the check section, and WNX is the net cross-section modulus about the cross-section principal axis of the check section. MX and MY are the bending moments about the two principal axes of the seam section, while gamma X and gamma Y are the plasticity factors about the two principal axes. It should be noted that for the following three cases, the plasticity factors gamma X and gamma Y are equal to 1. Firstly, the plastic development of the beam column under a dynamic load is not considered. Secondly, for a built-up beam column bent about virtual axis, the plastic development is not big, thus could not be considered. Thirdly, when the compression flange width to thickness ratio is greater than or equal to 13 times the square root of the ratio of 235 to Fy, and is less than or equal to 15 times the square root of the ratio of 235 to Fy, the plastic development could not be considered. Similar to the axially loaded member, the stiffness of the member under combined axial forces and moments is usually measured by the maximum slenderness ratio. That is, the maximum slenderness ratio of the member should be less than or equal to the allowable slenderness ratio of the member. The allowable slenderness ratio of the member is the same as that of the axially loaded member. In this lesson, we have studied the strength and stiffness of members under combined axial forces and moments. In the next lesson, we will learn the global buckling and the local buckling of solid web beam columns. See you next time.